the average value or the mean value of a function, the integration of even and odd functions, using definite integration for finding annuity amount, and using definite integration for finding present and actual values. The mean value theorem, or the average value of a function. The f of x is a continuous function, and it exists over a closed interval from a to b. So the average value will be given using this formula that we will use to obtain or to evaluate the mean value of a function, of a continuous function f of x over a closed interval from a to b. In other words, we may interpret the average value as, in other words, there exists a value c, x equals c, in between a and b, the interval a and b, such that the function has an average value or a mean value, like you know. So we will integrate the definite integral from a to b for the small f of x, you getting its antiderivative, which we denote by the capital F of x, and we substitute by b and then minus substituting by a. So this would act as so the average value 1 over b minus a, and then the integration from a to b f of x dx. And what we do in the integration is that we get the antiderivative and we substitute the x by b, and then we substitute it by a over b minus a. This gives us the average value for any function continuous over the x and y in a closed interval. So let's say that's the f of x. There exists a value c inside the closed interval from a to b, such that the function has the corresponding value f of c, which we call the average value of the function. Okay, in worksheet 10, exercise 1, we are asked to find the average value of the following functions over the given intervals. So we will go through applying this formula. The average value is going to be 1 over b minus a. We are given the closed interval from a to b and the f of x. So by direct substitution, we got b minus a, which is 1 minus 0, and the integration from a to b, so it's from 0 to 1, for the given f of x, which is x squared e to the power of x dx. Now it turned to an integration problem. 1 over 1 minus 0, that's 1, of course, and we can just rewrite the integral of the x squared times e to the power of x dx. Now this integration, if we want to solve it, we will think like we did before. Is it a function beside its derivative? The answer is no. Is it a function and above it there exists the derivative, which is solved as the len of the function in the denominator? The answer is no. So we have to solve it using the biparts technique, where we divide the integration of the two factors or the two operands into u and dv. And then the integration here is solved as uv minus the integral of v times du, which is a more simple integration, and go in the direction of solving the bigger integration that we are about to solve, the u times dv. So here, as we said, we will choose u as the function easy to differentiate, which is x squared, and we'll get the rest of the function as the dv, which is e to the power of x dx. And then we differentiate the u into u dash into 2x, and we integrate the v. So here we differentiate the derivative, and here we integrate the integration. The integration of e to the power of x is e x to the x, and its derivative is the same. And we said that there is a shortcut to this problem when the u is a polynomial, so we get the benefit from that, and we keep differentiating till the 0, and then we keep here integrating the function as much as we differentiated, and then we say that we have this table where we can construct the solution directly without using the integration again and again. So using this table, the average function can be written now as the product of this diagonal, which is x squared e to the x, and then minus, because this minus exists in the formula, so it's positive, negative, it's alternating, and then minus this product, which is 2x e to the x, and then plus that product, which is 2 e to the x, and then plus c if it was indefinite integral. Now this integral is definite, so we will substitute from 1 to 0. Substituting by 1 here for x is going to be 1 squared and e to the power of 1 minus 2. The x is 1, so it's going to be 2 and e to the power of 1 plus 2 and e to the power of 1. And then we have e here. And then we subtract, substituting x with the 0, the lower bound or the starting point. So 0 times anything is 0, 0 times anything here as well is 0, so we got here 0 minus 0, and then plus, take care that e to the power of 0 is 1, so this product is 2, and therefore solving this, we got here e minus 2. We can leave the solution like this, or we might get its equivalent decimal in order to make sure or double check it with the calculator as we did before. So this is simply the average value that where we apply the formula and we get the average value of the function. You will find here part B for your practice. It's exactly the same if we revise that from the solution. So part B again here we have from 0 to 2. So A to B is 0 to 2. We will direct substitute 1 over B minus A. And then from A to B, this function and this integral we have solved before, integrals like that where we have a function carries a power and then the derivative of the function, part of it exists, and the other part, which is the constant, we need to fix it. So we multiply by -2 inside and divide by -2 outside, and therefore this negative with the negative goes, and we have 1 over 4 as an extra amount outside the integral. No, here this negative will not go with that negative. This negative is from the f dash. It constructs the f dash, so it goes with the integration with the stretched s operator and the dx. And the function under the root is updated, the power, and then we direct substitute to get the average value by 4 over 3. In exercise 2, we get a different function, and we are asked to get the average value also from x equal 100 to x equal 500. So we direct substitute and get the equivalent value. Let's have a look over exercise 3, where it's a bit different, of a different idea. So here what we have is find the values of b such that the average value of the function is given as 2 plus 6x minus 3x squared on the interval from 0 to b is translated into equal 3. So here we are given the average value. We know that the average value of f of x over the closed interval a to b is given by 1 over b minus a, and then the integral from a to b for the f of x dx. So by direct substitution here, we have from a to b, it's from 0 to b. So we can say that a is the 0, and b is called the b, kept the b, and f of x that we have is this function. Let's substitute 1 over b minus a, which is b minus 0. We can write it as b. And from a to b, which is 0 to b, the f of x, which is given. And we are given also the average value, which is equal to 3. Now we are required to get the b. It turns again to an integration problem. So let's get rid of that b. So it's going to be 3b. We will move it there with the multiplication. And the integral here now is alone in the right side. Of course, this integral is a direct one where we have elementary functions and we can integrate each alone, separated by addition and subtraction. So the integration of 2 is 2x. The integration of 6x, the 6 drops and the x is x squared by 2, minus 3, the 3 drops and the integration of the x squared is 3 over 3. And we will substitute with the upper bound minus the lower bound, substituting with the b for the x with the b. This becomes 2b, and we can simplify the 6 and 2 with 3. So we'll get plus 3b squared minus, and the 3 goes with the 3 as well to become b power 3. Substituting the x by 0, we should subtract here the 0. And of course, 0 times anything, 0 again here times squared times 3, and then 0 cubed, all of this is 0, so it goes. So finally, we will have this formula where we need to solve it with algebra. We might take that b cubed to the other side to carry a positive coefficient. The 3b squared has no like term, so it will go to the other side with its opposite sign. The 2b as well will go and be combined with the 3b to have plus b, 3 minus 2. Now simplifying such a term, we can, if we have b, and b, so we think always of getting a b as a common factor, and we will be left with b squared, and we have taken b from here, so we are left with 3b, plus we have taken b from there as well, as we will be left with 1 equals 0, and then we can factorize. So here if b times this brackets is equal to 0, so it's either b is equal to 0, or we factorize using the mod and then 5, and we choose number 3 for factorizing a quadratic. The coefficient of b squared here is 1, and then equal. The coefficient of b is negative 3, equal, and the coefficient of the free term is 1, and then the equal. For the factors, we'll got 3 plus root 5 over 2 and 3 minus root 5 over 2. This value is positive and that value is positive as well. So if you want to get the decimal, this is 2.6 and the other x is 0.3, and b here represents the end point, or it's the upper bound. So the interval starts from 0, so of course it can't end by 0 as well. So we will reject this value, and we will go with these values as possible values of b. So the solution here is for the b2 or the b3. That's the final solution. So the a can be given or be required. We might have another problem where A is the required and B is given, and we will go through it the same way. Now we recall the even and odd function and some of its properties. We remember that the even function was symmetric, has a symmetricity along the y-axis. So we have here what happens after it happens below it or in the first quad, repeats in the second quad, also in the third quad, happens in the fourth quad if we extended the x and y axes. So algebraically we said that if the f of negative x is equal to the f of x, such that we have the function, the same function appears at negative x as it is for the f of x. This is the geometric and that's the algebraic. If we have the integration of such type of a function from negative constant to the same constant, we can rewrite this integral and make use of that the function is repeated, so we can just integrate from 0 to a the f of x, and we add, I want a space before it, so it's from 0 to a for the f of x dx, which is even, and then we add 2. So we can just calculate or evaluate the integral from 0 to the a, and then we multiply it by 2 because it's exactly the half of the area under the curve from negative a to a. Also for the odd functions, we know that the odd functions has a symmetricity along the origin, and it would look like this. So algebraically also it was the f of negative x, which is equivalent to the negative of the f of x. So the function at negative x is exactly as the function at x, but with the opposite sign. So if we carries here the integration from negative a to a for such a function, what we would say about the area under the curve. We have here an area under the curve with a positive and the same area with the negative, so they both cancel each other and the integration is 0. So whenever you see an integration which you feel it's not straightforward, and the integration boundaries are from negative a to a, and you suspect the function to be odd, you can just show that it is odd algebraically, and then you can say that hence that integral is going to be 0. Let's take these two integrals from the worksheet, exercise 4. So here we need to integrate this function from negative 3 to 3, and the other one also. Let's start with this one. So we will say, because it's from negative 3 to 3, we need to say to see whether it's an odd or an even function. So we will substitute every x with a negative x like we did before in worksheet 1, minus 2 to the power of negative x, and then we simplify out the sign, the negative with an odd, this keeps the sign, the odd power, minus times a negative 2 times negative x, that's positive 2x. Now, is this equivalent to the f of x? No, this is not equal to f of x, which carries positive in the x cubed. Okay, we have to double check the negative f of x then. The negative f of x, so we will put the f of x with opposite sign. Now, is this equal to the f of negative x? Yes, that's equal to the f of negative x. So here we can conclude that it's not an even, right? And here we conclude that it's not an odd function. It's an odd function. If f of negative x is equal to the negative f of x, then it's odd function. And if it's odd function, then the integral from negative 3 to 3 for the x cubed minus 2x dx is equal to what? Is equal to 0. Let's discuss the other integral here from negative 4 to 4 also, and we need to see whether this function is even or odd. So we will substitute every x with the negative x, and then we apply the function as it is multiplied by 5 and raised to the power of 4. Here the even power will cancel the sign, and we will be left with 5 times x to the power of 4, which is equal to the f of x, and therefore the function is even. This integral can be rewritten as 2 from 0 to 4, and then 5 times x to the power of 4 dx. Of course, the 2 and the 5 are extra and they are coefficients to the integral, so we can carry them outside, and the product is 10. And then we integrate only the x to the power of 4 dx, so we get 10, and the integration of x to the power of 4 is updated as well as long as the power is not negative 1, so we add 1 and divide, and then we substitute by the 4 and 0 in order to get the result, which we can double check here in the solution. It's 2048. That's it. Very well. Let's move to the other exercise. Here we need to find the amount of an annuity with income function C of t equals, the C of t is the income function and the interest rate. Let's have a look over the annuity formula from the lecture. These exercises for the average value. I hope that you're able to solve it now. This exercise is important, where we are given the unemployment rate in Greece since 2010, and T is the number of years after 2010, which means that we have a timeline starting from 2010. According to this model, what was the average unemployment rate in Greece between 2012 and 2015? So 2012 is how far of 2010? Yes, it's 2 years apart. And 2015 is 5 years apart. So we can use 5 instead of 2015 and the 2 instead of the 2012 for the t parameter. And therefore it's going to be 1 over 5 minus 2, and then from A to B, from 2012 to 2015, represented in the t timeline from 2 to 5, and the function will be copied as it is. It's all of a simple integration, simple power rules. If the power is not negative 1, we add 1 and divide, and then we would calculate that integral and then substitute with the boundaries. Here the average value is the same idea. And then this discusses the integration of the even and odd properties. So the annuity here is a sequence of equal payments made at regular time intervals over a period of time, which means like it's something like the retirement plan, where you are paying an income, whether it's a fixed amount you pay yearly, or someone pays it yearly, or like quarterly, or in different periods of time for a period of time. Afterwards, he's going to get these payments again, and we are here about to calculate this annuity using that formula, where the R is the interest rate. It's compounded continuously. We can link this to the compound interest we have solved before with the differentiation. However, the T is the term of annuity, or the period of years given in years. The C of t is the income function, and then the R and the T here is exactly the same. The small t is the T that we are going to integrate. So this is the formula that we are going to use, and you're going to find it in the formula sheet. And then let's take the exercise 5 from the worksheet. Find the amount of annuity. It's a straightforward and a direct exercise to find the annuity, where we have the formula with the income as a constant function by 2000, and the interest rate is the 3%, which we transfer into a value to become 0.03, and the term, which is the amount of years, given in years as the 15 years. If it's given some in years and some of the time in months, so for example, if it's 15 years and 3 months, so we will transfer the months into years. We have how many months in a year? 12. So we will divide here by 12 to have 1/4, and then we'll add 15 plus 1/4 in order to have the full amount of years. So we can transfer by that way the term into years if it's given in years and months, and then we will direct substitute in the annuity formula for as e to the power of r, which is the rate, times the term, which is the number of years period given, and then the integration from 0 to 15 to the capital of T. C of T, which is the income function, it's always given. Here it's 2000 multiplied with e to the power of negative r, which is 0.03 T. That T is not going to be replaced. Only the capital T is the term, and the small t is the one to be integrated in that formula. So here, this integration, of course, it's direct. We can take this 2000 outside because it's a constant, and we have only to integrate the exponential. So we can carry this 15 times 0.03 is the 0.45, and then multiplied with the 2000 outside the integration, and the integration only carry now the exponential, where its integration we have done now several times this integral, and we divide by the coefficient of the t and substitute from 15 the t by 15, and then subtract by substituting with the 0. We can leave these constants outside, all of these constants, and then we substitute only in the exponential in order not to mess up with the calculation, or we can directly do it in that part. After we calculate, we can double check with the calculator as we said before. So now we can substitute the t by 15, and then substitute it again with the 0, and take care that 0 times anything is 0, but the 0 in the power of e is 1. So this is going to give us the final value, which is approximately 37,887. And it makes sense if someone pays $2,000, for example, for 15 years for an interest rate of 3%, this amount is going to be, after 15 years, 37,887. So it makes sense as a retirement plan for 15 years that one would get at the end that amount of money. So in the worksheet, we have other exercises for the same thing, where we will use the same formula. Here, you deposited the $3,500 each year for 10 years into an individual retirement account, paying 9% as an interest. How much will you have in your individual retirement account after 10 years? So we are given here the term as 10 years, and then we have the deposit amount which is the income function, constant, 3,500, and the interest rate is the 0.09. So we direct substitute again, and we can evaluate the formula. So here, e to the power of r, which is 0.09 times 10. And from 0 to 10, that constant income function multiplied with e to the power of negative 0.09 and take care of the small t. It's not substituted with the term amount given. This term is instead the integrated t, and it's a direct integration for the exponential where we divide by the coefficient of the t like we did here. Of course, we can write it over the e, or we can put it here outside, because if it's a product and quotient, we know that we can rewrite this in terms of the algebra, and then we calculate the amount to become $56,762.3. So the payment of $3,500 for 10 years with an interest rate of 9% would become $56,762. Let's move to other economic expressions. The present value of the income over t years within an inflation rate and the actual value. So in exercise 7, we want to differentiate between two very important values, which is the present value of the income over t years. So the present value, or first the actual value, if you have a sum of money, its actual value is its value now. For example, if you won the lottery and you won like $1 million, and you are going to get them in installments like for 10 years. So every year you're gonna get a sum of it. The actual amount of this payment, or of all of the payments, is the 1 million, right? If we want to calculate this value, the value of this money after 10 years, for example, is going to consider or encounter the inflation rate. So under the inflation rate, it would the amount value would decrease or increase. The inflation rate is the تضخم, معدل التضخم. So its value is going to decrease, right? So the actual value will be directly the integration or the accumulation of the income function over the period of time. This doesn't encounter any inflation rate. But if we want the present value, for example, after 10 years or so, or 15 years, or any term of years, this one would include or would encounter the inflation rate. So it will have this exponential multiplied with the income function, and we will do that integration. Here we are asked to find the present value of the income, C of t given. Let's do it with part A is 5,000 constant. Let's do it with B, where the C of t, the income, is given as the 150,000. I'm not missing that, no, plus the 2,500 t, where the R is given as the inflation rate, as the 4%, and we know that the percent we prepare to use it and turn it into a value to be 0.04, and the t, or the term, is given by 10 years, so we can use it directly because it's given in years here. If we need to get the present value, so it's equal to the accumulation from 0 to 10 years for e to the power of negative r, which is given as 0.04 times the t term, multiplied with the income function, which is 150,000 plus the 2,500 t, This is the function dt. So how can we solve this integral? If we have like an x multiplied with a bracket of the sum of two terms, of course we think of distributing that here and there, and therefore we have two integrals from 0 to 10 for the exponential. We can write this as negative 0.4 and then multiply with the constant plus the e to the power negative 0.4 also multiplied with the other part, the other term, with respect to t. So what's the integration of the first part? That's a constant that will drop, right? So it's 150,000, and then the e here it carries is a constant as well. Do we miss a t here? Yes, we missed a t here. So this t, this is not the capital T, this is the small t. So here we have still the 0.04 as the inflation rate multiplied with the t, and here as well, and here 0.04 t. I'll correct this with the. So here we direct substitute the r, but the t, the small t, it's not substituted as I told you. It's the one that's going to be integrated. So here we have this t. I'm not used to this economical formulas. So here we will keep that t because this t is going to be integrated. So here we have the integration of e to the power negative 0.04 t times this constant. The constant will drop, and the integration of the exponential is itself over the coefficient of the t. And then plus, here we have the 2500, and then the integration of t and e to the power of t. Okay, this integral needs to be solved alone, so we need to keep it as an integration, and then we might call it like I1 and go to solve that I1 and then substitute its result. So let's call this I1, because as you may figure out that this integration includes a t which act as x in our integrations, and the e power negative 0.04 t, or with respect to x dt. So again, we think here about this integral. Is it an f multiplied by its derivative? No. Is it a derivative over the f? No. So we have to work over it as by parts, where we will choose u as the t, the polynomial, and dv is always the exponential, because the exponential is always easy to be integrated, so we use it as the dv, where we integrate here. So we will divide with the coefficient of t, right? And here we differentiate, so we can simply write u dash, which is 1, and then we can move till the 0 like we did before, or because this integration, if we have a look over the horizontal integration here, so it's going to be u times v, the result, minus integration of v times the derivative of u. So from these two lines, the I1 is u times v, which is t times e to the power negative 0.04 t over negative 0.04, yes, the product of u times v, minus the integration of 1 times that function, and we have just integrated that function. So 1 times this function is going to be exactly as it is. We can take the negative 0.04 separated, and the integration of the exponential is again the same itself divided by the coefficient of the t, right? So here I've rewritten this, I've seen this as if it's A over B. I have taken 1 over B away of the A, and then applied the integration over the A, which is the exponential. The integration of the exponential, like we integrated that part, is itself, it drops, divided by the coefficient of t, right? And therefore, this is the integration, and we need to direct substitute from 0 to 10 because it was definite, from 0 to 10, and here as well. So here we need to substitute by 10 minus substitution with 0, and here as well. So after direct substituting, I'll double check the final value. So we will go to mod 1, and then we can apply the integration. It's x, so we will use the x multiplied with its times. Don't rely upon the smart, these machines are not smart. So we will add the times and then minus 0.04 x instead of t, and then we carry the limits, which runs from 0 to 10. Now it's x times e to the power negative 0.04 x, that's correct. So the value is the 38.46. So this is the value of the I1, which we will put here and plug in it here, and then we multiply it with the 2500, and then we add this amount after substituting for the t by 10 and then by the 0. Don't forget that this amount was definite integral from 0 to 10, so we will direct substitute the t here as well by 10 and then by 0, and we keep these constants outside. After this, after we apply this and that and the substitutions, we will get here this as the final amount, where we can read it as 1,332,474.727. So this is the outcome of paying, or this is the present value of this income function that we used over the term of 10 years with an inflation rate of 4%. This is not a constant. The income function here is not constant. So we can't direct compare between this amount and that one. But if we calculated the actual value, we will find it a much higher value, because the actual value doesn't include the inflation rate, right? معدل التضخم, it doesn't include it, and therefore it's going to be a higher value than the present value. Okay, let's move to the to exercise 9, or exercise 8 first. A company expects its income during the next 10 years to be given by C of t, that's the income function, C of t, assuming an annual inflation rate. Okay, so let's get out the income, which is 5,000 plus the 25t e to the power 0.1 t, and the then assuming an inflation rate first for the term, which is 10 years, right? It was given here, and then this is the income function, And then we have the inflation rate, which is 10%. So the rate is equal to 10%, where we will prepare to use it as a value, and it becomes 0.1. For the following, find the actual value. Okay, for the actual value, if we call it AV, so the AV is the accumulation from 0 to t for the income function dt. We have here from 0 to 10, c of t is the given function. We have here t multiplied with exponential, so we have to apply one time by parts. This integral is divided into these two terms, where the 5,000 integration is itself multiplied by the t, and we substitute for the t by 10 to 0, and then plus the 25 times the integration from 0 to 10 as well to the t e to the power 0.1 t dt. Let's take that integral and call it I1, this integration, and calculate it here. So if I1 is the integration from 0 to 10 for t times e to the power 0.1 t dt, this function is not the derivative. None of them is derivative of the other, so we'll call one as u and the exponential as dv, like we are used to. And then we differentiate the u to have 1, and we integrate the v to have the same function because it's exponential divided by 0.1. And then we apply the by parts technique, where we multiply u times v minus the integral of v du. So the I1 is u times v, so it's t times e power 0.1 t over 0.1, and we substitute that part by 10 minus 0, don't forget this, minus the integration of 1 time that thing, that term, I mean. So we can take the 1 over 0.1, and instead of integrating it again, write it with the integration. And of course we can write it, if you're going to carry it, I can write it first. This is over 0.1 dt. There's a decimal point here. Yes, and then the integral is going to be this part as we substitute by 10 minus substituting by 0. We take the 1 over 0.1 outside of the integral, and we have here inside the integral only the integration of e power 0.1 t. So this integration is the same t over the coefficient of t. And then we substitute here also the t by 10 minus by 0 to get the amount at, the amount will be 50,500. This is for paying this income function for 10 years with, of course, the actual value doesn't encounter the inflation rate. Now let's get the present value, which is the value after 10 years for this amount. Of course, we expect that the value becomes less. So now we would integrate from 0 to t, the e to the power of negative r t times the income function dt. By direct substitution, we have the integration from 0, and the capital T is the 10 years, the e to the power of negative, the rate, which is 0.1, times t, this t, the one that's going to be integrated, so we are not substituting it, and then multiplied with the income function and we put this in between brackets for carrying the sign, for keeping the sign correct, and this is going to be integrated with respect to t. Now let's keep this amount and go in integrating that function. Now again we have a term multiplied by the sum of other two terms in a bracket. So because this one includes a t, it's not only a constant, it has to be encountered inside here instead of finding out this as a function and the whole bracket as another function. So we will simplify it first, and the integration becomes, we can take the 5,000 outside as a constant and the integration of the exponential inside the integral from 0 to 10, and then plus the 25 outside because it's a constant, and inside the integration, let's have a look, we need to multiply e to the power negative 0.1 t, and here it's e to the power 0.1 t. When we have the same base and different powers in a multiplication, we can rewrite them with a common base, and we add the power. So negative 0.1t plus 0.1t, this is e to the power of 0, which is 1. So here we only have the t dt. The product of e power negative 0.1t and e power 0.1t goes together as 1, and we are left only with the t. And of course this integral is a direct one where we have the 5,000 and the integration of the exponential which is negative 0.1 t divided by the coefficient, and then plus the 25 and the integral of the t, and we substitute in both the t by 10 then by 0, and then we have the final solution. We can write this into the calculator after that to double check our solution, but we have to show that we substitute the upper bound and then the lower bound like it's shown here in the solution 5. So we have at the end this amount which got to be less than the actual amount, of course, because this is the amount after 10 years considering the inflation rate. Now we have two extra problems about the integration. Let's solve them in this worksheet. We need to find the definite integral from 1 to 5. Okay, for this given f of x, and the f of x then is described as a piecewise function of two pieces, one that starts from 1 to 3. So from 1 to 3 we have this function working x power 2 plus 1, and from 3 to 5 we have this function, other function working 5x minus 1, right? So in order to integrate from 1 to 5, we need to divide this integral into two parts. You remember this property from a to b for f. We can divide it from a to c and integrate the f, and then from c to b, f dx. This if c is between the a and b. And of course the f got to be continuous function as well, which we will always have, like we have here two polynomial functions. So we can say that this integral from 1 to 5 f of x dx can be solved from 1 to 3 with a working function x squared plus 1, and then we add from 3 to 5, and what's the working function then? Yes, the 5x minus 1 dx, and both are direct integrations. The x squared is going to be x power 3 over 3, and the integration of 1 is x. We'll substitute by 3 minus substituting with x by 1, in addition to the 5 here would drop, and the integration of x is the x power 2 over 2 minus the 1 is the derivative of x, and we substitute here by 5 minus substituting the x by 2, and then we get the final solution. We can double check the final solution here. First, we can write the x squared plus 1, and the integral is from 1 to 3. That's 32 by 3. And then plus the other integral, which is 5x 5, and then alpha x minus 1 from 3 to 5. That's 38. And then we sum up 38 and 32 by 3. We would sum this with the 32 by 3. 146 over 3, or this decimal form. We can take up to 2 decimal places. Here it's given as 48.6. So that's the final solution. The other exercise is very interesting because it uses the definite integral properties, the other two properties. So here it says, if we have the integration for f of x from 1 to 8 is equal to 10. We said that the geometric perspective of the definite integration is the area under the curve. So whatever f is not given here, we know that the area under that curve from x equal 1 to 8 is given by what? The area under that curve, whatever what it is, it's equal to 10. And then we are given also that for the same f, which we are not given, from 4 to 8 is negative 2. So from 4 to 8, this amount is negative 2. Use the properties of definite integral to evaluate from 1 to 4. So we have discussed the other property that from a to b can be divided from a to c and then from c to b if c is enclosed by a and b and f is continuous. So you can say that the integration from 1 to 4 of f dx is equal to the integration from 1 to 8 of the f dx, and we subtract from 4 to 8 of the f dx, right? And hence we have 10 minus the negative 2, which is equal to 12. And then we are required to find the integration from 4 to 1 f dx, and we can say that this is exactly the integration from 1 to 4 with the opposite sign, which we have just calculated above, so it becomes negative 12. This is a simple exercise which illustrates the properties of the definite integral. We are not given here the function, and we didn't need it to evaluate the required integration. Now that was the end of that worksheet. We have these formulas that we are going to use for the average value, the annuity, the actual, and the present values.